Hi, everybody. Happy Wednesday. Welcome back to another session of AP Calculus AB Review. And this week, we are going to look at the beginning of integration. So moving away from differential calculus and into integral calculus, we're going to cover some of the basic background conceptual things for integration. So for those of you that have not joined us yet, hi, my name is Leah. I'm very happy to be doing calculus with you. Couple of just logistical things here. Your microphones are off. I can't hear you at all. So if you have a question, there's a chat feature at the top and a Q&A feature at the top. You can use either one of those and I will get your questions. I will try to answer them as we're going. If I don't get to it or don't give a detailed enough answer, we can talk through more at the end of the session, or you can always email classes@prepmatters.com. That will be at the bottom of the screen when we're actually working, and I will give you a more detailed answer then. So we are going to go ahead and get started in about a minute, and we will jump right into that integration. Also, as a reminder, or just new information for those of you that have not yet watched any of these videos, I'm writing off of my screen, so I'm going to take my camera view away from my face for a little bit so that you're not staring at my ceiling. But again, I will come back at the end and talk to you face to face, and then please do send in those questions as you have them as we're going so that we can talk through different things as they come up. So before we actually jump into this AP Calculus Unit 6 information, again, this is the beginning of integration, I do want to go just slightly review some of the differential calculus pieces. So this is where we're going. But before we do this, let's very quickly look over some of these big ideas of differential calculus that you see on this page. This is what we've already covered in the last 3 sessions. If you have not watched any of those or want to go review any of those, you can access them via the Prep Matters YouTube or the PMTV page of the website. So here you see the main ideas that we talked about in these 3 sessions. And I want you to just quickly glance through this list and ask yourselves how you feel about doing each thing. So ask yourself how you feel about actually doing this, but then keep going. This is the part that we usually skip. Keep going, and more importantly, ask yourself how you feel about explaining each thing. So for example, if you look at this last bullet point here, solving optimization problems, we need to be comfortable with solving an optimization problem in order to really do well on this free response style AP exam. But we also need to be comfortable understanding an optimization problem. So this means that we need to be able to extract variables from a question and write an equation that relates them, then figure out how to use a secondary equation to eliminate a variable if our first or primary equation is in terms of several variables. Then once our primary equation is in terms of only one variable, we need to differentiate it with respect to that variable, not with respect to time, which would be a related rates problem situation, but with respect to the actual variable in the equation. Then once we do that, our goal is to figure out where this derivative function actually equals 0, to solve for that value, to confirm that it really is a maximum or a minimum, and then keep going, keep talking to yourself. Why do we need to do that? Why do we need to figure out where the derivative is equal to 0? Why do we need to actually prove that something is a minimum or a maximum? We don't just want that to be some kind of step that we memorize in a process of an optimization problem, but we really want to be able to confidently explain to someone else why we need to figure out, for example, where the derivative of an equation equals 0. So that's what I mean by that. That's what I mean by that. Look at this list of these differential calculus things and make sure that you could confidently, theoretically explain what it means, explain the background, explain how to do a problem, and explain why to do a problem. If any of this is something that doesn't look like you're ready for that, looks like you need to go review a little bit more. Again, you can go back and look at recordings of those sessions, dig out your AP Calculus notes, dig out your textbook, and kind of dive back into the theory behind some of this information. So now let's just dive into integration. And just like we started differential calculus with the theoretical concept of a derivative, we want to start here with the theoretical concept of an integral. So it is great if you can really quickly find a requested integral of a function, but that is a quick multiple choice question, and we are not getting those. So free response questions, we know, weave through a lot of underlying ideas of calculus and really force you to make jumps and connections before you even get to the point where you can do the easy math. Before you even can evaluate an integral, you have to sift through all of this other information first and figure out that the question is even asking you about an integral. So we'll start by talking about the concepts first. So let's start talking about the concept of integration using this function here. And I'm only going to look at the parts of the function between a and b, which I already marked on this page. Now, if I actually bound this function here by the lines x equals a, let's pretend that's a really beautiful straight line, and x equals b, I've created a solid that has 4 sides, and I'm going to use sides as a loose term because this top is not super pretty here. So I created this solid. And essentially now, if I took away the axes and I took away any form of position on a coordinate plane, I just have a 2-dimensional solid from the world of geometry. And in the world of geometry, what we really focus on is finding area of a shape. So if we say our goal here is to find the area of this shape, ignoring the axes, ignoring the position, ignoring the actual function, theoretically, hopefully, we could do that. Of course, we run into issues here because this is not one of the nice, beautiful shapes that we have an easy area formula for. It's not a rectangle or a triangle or a parallelogram or a circle or anything else from that geometry, ACT, SAT world. So just like any time that we run into a problem like this, a problem where we want to do some basic math, but we don't necessarily know how, we need to turn to what we know. And just like when we tried at first, a long time ago, to find the slope of a tangent line, but we didn't have the ability to yet, we used the slopes of secant lines because we knew how to do that. Same thing here. I can estimate the area of my shape using shapes that I do know. So for instance, I can fill my shape with rectangles. I already made this nice and pretty for you. So we could fill our shape with rectangles. If we start with estimation using 4 rectangles, for instance, it's pretty nice and easy to physically see the error in our estimation. If I now find the area of these 4 rectangles, well, I have extra. I don't really actually want any of this. I have extra there, and I'm also missing this. We can physically see the errors. So this is obviously not a perfect system, but the more rectangles we use, the closer our estimation will be. So if I make more rectangles, physically look at how our error isn't as great. I'm just missing this little part here. And then this is not perfect, but then I have some extra here. But in the least mathematical words that I can use right now, I have less extra than I had above. And as we use as many rectangles as I can possibly physically draw in this same function, we almost don't see any error at all. I can't even make little purple squiggles here because I don't have enough space to actually put a pen marking in my error. We're almost eliminating this error by using more and more and more rectangles. And this is the concept that you know of as Riemann sums. And ultimately, if we have as many rectangles as possible, we should be able to get as accurate of an area of this shape bounded by side, x-axis curve. We should be able to get as close to an accurate estimation of the area of this shape as possible. So again, just like we used slopes of secant lines, that just kept getting shorter and shorter and shorter and shorter to estimate the slope of a tangent line, also known as the derivative. We can use areas of rectangles that just keep getting kind of skinnier and skinnier and skinnier in order to fit more and more and more in a shape to estimate the area under a curve or the area of this 2-dimensional shape. So in calculus notation, that looks like this. So I'm going to say, let me actually go back to this. I'm going to say this area here, this area of my shape is called A. So A is going to be equal to the area of all of these rectangles added together. And I want those rectangles to be as small as I can possibly make them. So I'm going to take the sum of the area of lots of rectangles. And the area of those rectangles would be length times width, or base times height, however you want to think about this, where the height is the actual function value. I'm going to give this a subscript so that I can properly write a summation here. And the base is the difference between x values. And I want to do that all the way from 1 to n, where I'm saying n is my number of rectangles. And I want n to get as close to infinity as possible. So just like we had a limit definition of a derivative, we almost have a limit definition of an integral as well. Now, a couple of quick notes. I'm going to zoom out so that you can stare at all of this at one time. A couple of quick notes here, and everything that I just did in this very quick, broad overview of this, I used left-hand approximations for my rectangles because I used the height of each rectangle at the left side of each interval. So here, if I have my interval, I have 4 intervals, so let's see if I can properly count today. 3 comes after 2. So 1, 2, 3, 4. I used the height at the left side of each interval to actually generate the height of the rectangle. If I used instead, let's see how many colors I can put on one thing at one time. If I used the height at the right side of each interval, so for my first rectangle, I used this height, second rectangle, this height, third rectangle here, and fourth rectangle here, that would be a right-handed approximation for this particular function. In this case, in this particular function, that right-hand approximation would be an underestimate. We would be missing a lot of area, whereas in this particular function, the left-hand approximation gave us an overestimate. We can typically the AP exam asks for one or the other. They tell you to do a left-hand or right-hand approximation. Occasionally, you could use a midpoint approximation. This generally appears in textbook work throughout the year much more than it appears on an actual exam. But if that were to be the case, you would need to know a little bit more information than this. But if that were to be the case, you would use the height of the function at the midpoint of each interval. So we would use, let me pick something that doesn't have red all over it. For this rectangle between 2 and 3, for instance, we would use this function value right there. We can also change shapes. There are trapezoidal approximations. There are other types of approximations, but this is the most basic concept or most basic idea. And if you conceptualize this, it'll hopefully not be too bad to apply to anything else. Also, just quick note, and this will come into play when we do an AP problem, and then I promise I will stop drawing all over this same picture. I made my intervals, my delta x's, all exactly the same width or as close to the same width as I could physically draw. They don't have to be the same. Intervals for a Riemann sum or a rectangular approximation don't have to actually be the same. And we will, again, we'll see this in an AP question in a little bit. Okay, so now let's actually connect that to integration. So just like we had our limit definition of a derivative, we just created our limit definition of an integral, kind of. I'm going to refine that in a minute. The integral from a to b of f of x, so let's write that out. The integral from a to b of f of x with respect to x is equal to this limit definition of the approximation of area that we just talked about. So the integral from a to b of f of x with respect to x is equal to this limit that we just did. The limit as n approaches infinity of the summation from I equals 1 to n of our areas of rectangles. And I'm going to do this formula-wise right now just because it's a little bit easier, as if all of the widths of my intervals are the same. This delta x, I'm just pretending it's the same every single time. It's the easiest way to write the formula. And again, what we're trying to concentrate on right now is understanding where this all comes from, not fixating a ton on the actual formula, but conceptualizing what's really going on here. So I'm going to relate my integral right now, and then we will pull all of this together. I'm going to relate my integral to this area of all of these rectangles added together when I have an infinite, or as close to an infinite as possible, number of rectangles. Extra fun fact here for you, this symbol, an integration symbol, looks like a super fancy S because it represents a sum. It represents a summation. That is why it is that actual attempt at a letter S. And then also information here, the dx doesn't actually have any meaning on its own. It's not a standalone value, but it's a connection to the integral sign. So these two pieces need to be together all the time. We have to know what variable we are integrating with respect to. That's what the dx tells us. It tells us that we're integrating with respect to x. It doesn't have standalone meaning. And if we didn't have it, then the integral sign doesn't actually have its full meaning either. So those two pieces do need to be together all the time. So this tells us here that a definite integral of a function between 2 points can be interpreted as the net area between the curve of f of x, or the net area under the curve of f of x between 2 points. So between points A and B. And I say net area here because using a Riemann sum approximation with function values as heights is going to give us negative area if that function is under the x-axis. So if we look at this function here, and I'm just going to make point A 0, if I start doing Riemann sums, if I start thinking through this approximation of the area, I'm going to keep saying under, but area under a curve, area between a curve and the x-axis, whatever you want to think about it for now. If I do that, even just drawing in one rectangle here, when we look at this, the height of this rectangle has a negative value. We're getting a negative area. So what happens overall, see if I can get rid of just this green line. Yep. What happens overall is that this piece of the function here, all of this ends up with a negative area, and this ends up with a positive area. So when a function takes both positive and negative values, just like this example right here, then the integral can be interpreted geometrically or conceptually as the difference of the positive areas of the various sections of the graph. So if you do think about everything as a positive area, so let's say for instance A1 and A2, then the integral geometrically can be interpreted as the positive area A2 minus the positive area A1, if you want to think about just combining positive areas. All right, now indefinite versus definite integrals. I want to do a quick comparison of this, but I want to add a few quick properties here before we even get into this comparison. So a couple of properties of definite integrals. Again, keep in mind that geometric idea. It's not perfect yet, but geometric idea of definite integral area under a curve. And some of these properties hopefully will flow through pretty naturally, or just pop back into your brain from whenever you learned them in class. So first important one really just tells us that we can break an integral, a definite integral, into pieces. So if we're looking at the integral from A to B, and we know that we have a point C right in the middle of A and B, then we can break that integral into two pieces. I can say it's the integral from A to C plus the integral from C to B. That seems hopefully geometrically incredibly obvious. If I have a rectangle and I want to find its area, I can find the area of two pieces of it and add them together. But in the actual context of algebraic problems, this is incredibly helpful. So just keep that in mind, as is the next one. The next one may be a little bit less intuitive, but if we integrate a function, if we're trying to find the area under a curve from A to B, if we reverse those limits of integration and instead go B to A, we can negate that and end up with the exact same thing. And that's really because your delta x, your width of your interval, is flipping around. Third one, hopefully super obvious at this point. If we're integrating from A to A, or trying to integrate from 3 to 3, for example, that would be 0. The area between 2 points that are exactly the same point doesn't exist. And then same thing that occurs with differentiation. If we have a constant in front of our function, and then we are trying to take the integral of a function, that constant can come to the outside. The constant can come out of the integration, which makes things a little bit easier. Okay, now I want to quickly talk about indefinite versus definite integral. Then we're going to tie everything together with an actual theorem. So big difference between an indefinite integral and a definite integral. A definite integral is a number. So definite integral, number. The definite integral is the integral that actually has bounds. The integral from A to B, the integral from 3 to 7, the integral from 5 to 100, whatever. When we do all of that math, we get a number. We get the value, the net area that we're looking for. An indefinite integral does not have bounds. An indefinite integral would lose would lose the actual bounds around the integration sign, and it would just be the integral of f of x, the integral of 3x plus 7, the integral of whatever. There are no bounds. And since there are no bounds, we are not able to fixate in and just look at one particular area. Area was a bad choice of words right there. One particular section of a function between a function and the x-axis. We don't have the left and right bounds. We can't focus in on one particular section. We can't end up with an actual number. So an indefinite integral is a function or a family of functions. We cannot start with an indefinite integral and end with a number. All right, now I'm going to start connecting lots of pieces. So an indefinite integral, an integral without bounds, really just represents the antiderivative of f of x. The antiderivative of f of x. Whereas the definite integral represents the net area under a function between a and b. So again, area, function. And that function, that indefinite integral function, is called the antiderivative of f of x. So what function would actually give us the derivative of f of x? That's what I mean by antiderivative. Once we put bounds on this, once we give ourselves some limits of integration, we actually choose x values to focus in on, then we can think about using the ideas of areas under a curve, and we can find the value of the antiderivative at b and the antiderivative at a and find the difference between them, which is what a definite integral is actually asking us to do. Okay, so I just made a lot of connections between things that we didn't actually explicitly connect via math yet. So now we're going to tie all that together with the fundamental theorem of calculus. Okay. So I just said above in the last slide that when we're evaluating a definite integral from a to b, we can find the antiderivative at b and the antiderivative at a and find the difference. And all of a sudden there we just have the net area between a and b. Why can we do that? We haven't actually connected integrals and derivatives yet at all. We haven't made the connection, other than me just physically saying the words, between integration and differentiation. So we need the fundamental theorem of calculus for this. So I'm going to step you through this theorem piece by piece so that hopefully it makes a little bit of sense. So let's look at this function here. So let's define f of t as the function 2t, so just a nice, beautiful linear function, so that we have this function here with these specific 4 points, along with many, many others that we're just going to not really care about for now. So let's look at the area under this curve between two values of t. So I'm going to define g of x as the integral from 0 to x of f of t dt. So I'm going to define g of x as my area under a curve between 0 to a specific point. So now, for example, that would mean that g of 0 is 0, the integral from 0 to, let's see if I can get my numbers under control today. The integral from 0 to 0 of f of t dt. The area under the curve from 0 to 0, well, that is 0. There is no area when we're just talking from point to point. That is exactly the same. But then we can keep going. The integral from 0 to 1 of f of t dt. The area under the curve from 0 to 1 of this function f of t. Now, I chose this nice linear function because we can easily geometrically do this. We don't need to know integration in order to find this area. We don't need Riemann sums. We don't need approximations. We just have this nice little pretty triangle. We find its area. Also, that is not at all right. Let's change this number first so that I can do this correctly. All right. Like I said before, I usually figure out my mistakes when I'm halfway through doing a problem. Found that one. Okay, so area here would be 1. Then we can just keep going. G of 2. Now I'm evaluating, here's my x, here's my x. Now I'm evaluating the area under this curve between 0 and 2. And when we do this, we end up with a triangle that has an area of 4. And if we just keep going, now I'm looking at the area between 0 and 3. That gives me a triangle with an area of 9. And then I can go from 0 to 4. That gives me a triangle with an area of 16. And if we look at what's starting to happen here, look at your points. When x is 0, g of x is 0. When x is 1, g of x is 1. When x is 2, g of x is 4. When x is 3, g of x is 9. When x is 4, g of x is 16. And that should be starting to look like a pattern that you should know really well. That is a quadratic pattern right here. And this is telling us that g of x is equal to x squared. I could just keep going with totally ignoring this, totally ignoring my diagram over to the left, and I can just keep going with this knowledge. Well, g of 5 is 25, g of 6 is 36. Great, this pattern is going to hold. But now here's the good part. Look at this. G of x is x squared. F of x, where we started, is 2x. And look at these together. Now it's really nice and easy to see that f of x is the derivative of g of x. So now we can start connecting differentiation and integration, or an integral and a derivative. So let's pull this together a little bit. I'm going to take this over here. And if we take this over here, I'm now going to be able to say that, let's use all the same things. F of x is equal to the derivative of g of x. Well, if we step through a chain of functions, we can make a lot more equality statements. So let's just say, for example, I start with my function f of x, and I just start differentiating. well, then I would have the first derivative of f of x and the second derivative, and so on and so on and so on. If I instead go up, I start integrating, then we end up with the antiderivative of f, which is generally written as a capital F. That's the exact same thing as saying the integral of f of x. Now, from this part that I already crossed out, let's see if I can uncross this out. From this part right here, I already know that g of x is equal to the integral of f of x. So there's another equality statement right there. The integral of f of x is equal to g of x. I can also just step through my function chain over here. Start with g of x, differentiate it again, differentiate it again, and just keep going. And by doing this, by kind of pulling this off to the side and explicitly creating this chain of functions, it's a lot easier to physically see the connection between functions that are written in different letters. So what I mean by that, when we have functions labeled as f and g in the same question in some kind of relationship. Just start with a function, start going down by differentiating and going up by integrating, and then set the second function to the right of the first function where you know you have a statement of equality. And then you just keep doing the same thing. Just keep going down by differentiating and up by integrating. So there's our connection between integration and differentiation. And the actual fundamental theorem of calculus, if I put this in proper mathematical notation instead of all of the things that I just said, looks like this. There's two pieces. Looks like this. I'll let you look at that for just a second. So again, what we just talked about, if I know that g of x is the integral of f, don't fixate a lot on the t versus x's situation. If I know that g is the integral of f, then f is the derivative of g. That integral differentiation or integration differentiation, integral derivative idea works like that. I also know here that if I am evaluating a definite integral between a and b, between 2 points, I'm going to end up, whenever I have that, I'm going to end up with a number. I can get that number by taking the antiderivative, or the integral evaluated at b, and the integral evaluated at a, and subtract those two. Okay, now to actually evaluate these integrals, I'm going to do this one kind of quickly. To actually evaluate these integrals, we need to know antiderivatives. This is not necessarily as easy as knowing derivatives. Derivative rules tend to be more common knowledge. For instance, if we just say, okay, what's the derivative of sine of x? Most people can rattle that off pretty quickly and pretty easily. Derivatives have a lot more kind of mathematical processes behind them. That is not necessarily the case with integration. We don't have product rules and quotient rules and chain rules. We just kind of have, hopefully we recognize a derivative and can move from there. We have a couple more tricks, but that's kind of the basis here. So for example, I'm gonna go through this one backwards. I put the hardest one first, so I had a lot of space. If we look at this last one, the integral of secant squared of theta, d theta, well, in this case, hopefully we can evaluate this right away because we know that the derivative of something is secant squared. That would mean that when we integrate secant squared, we're going up. We're trying to get the function that it is a derivative of. We could say, well, great, that equals tangent of theta because the derivative of tangent of theta is secant squared of theta. Now, since this is an indefinite integral, I need to end with a function, which I did, but I also need to add a constant because the derivative of a constant is 0. So I could theoretically have any constant right here and still differentiate this line and end up with this function. We can also fairly evaluate integrals if we have just a manipulation of what in the derivative world is the power rule. We can kind of undo the power rule. So we can evaluate this definite integral here using that knowledge. So for instance, I can write, so first of all, I can pull the 1/2 out, but then I can write this as the integral from 1 to 9 of 1 over x squared dx. I'm going to just write that with a negative exponent. And then we can essentially undo the power rule. If we were taking a derivative of something like, let me go off to the side here, of something like x to the 7th power, well, we would bring down this 7 and then subtract 1. So we need to do the opposite of that in order to get the function that gave us a derivative of this. So instead of subtracting and multiplying, we are going to add and divide. So I don't want that. So when I do that, I would get, instead of subtracting 1 from my exponent, I'm going to add 1. And instead of multiplying, I'm going to divide. So I would have x to the negative 1st power over negative 1. And I need to evaluate that at 9 and at 1 and find the difference between those. You can see that written like this. I don't know why my 1/2 is so far away, if we can put it closer. You can see that written like this, or you can see that just written sometimes as a really large vertical line right here. That means take this, evaluate it at 9, and then evaluate it at 1 and find the difference between them. Either one. I tend to use the brackets because it makes my math a little bit cleaner when I have constants out in the front. Up to you. You can do this one kind of either way. And I trust that you can do all of that math, and I want to show you more of the tricks and crazy things here. So let's move on to this one. So here, we don't have a lot of easy tools. Those are essentially our easy tools. We either recognize a derivative that we know, like we did with the secant squared, or we can reverse undo the power rule. That's pretty much it. With the exception of one more thing, which is integration by substitution, which works in some specific cases. It's kind of the chain rule equivalent of differentiation here. So I want to show you that really quickly. So when we're using integration, our goal is to rewrite part of the expression, part of the integrand, as another variable, differentiate that variable, and then eliminate all traces of our original variable. So what I mean by that, I'm going to say here, I'm going to look at my denominator. I'm going to say here that u, generally we use u, use whatever you want. Most of your classes probably used u in a u substitution here throughout the year. I'm going to say that u equals 1 minus 4x squared. And then if I differentiate u with respect to u, I would have negative 8x dx. I still need to actually differentiate that value of x. And that works for substitution because once I substitute, all of this is going to become u, and this is going to become a manipulation of du, of the derivative of u, which means that I can rewrite this function as 1 over the square root of u. And let me just do one step before that, actually, to make this way more clear. Let me divide this. By the negative 8. So now I can replace this x dx in the original by du over negative 8. And I'm going to go ahead and pull out the negative 1 over 8. And now I have this function here. And that this inside part right here, now would be a manipulation of kind of undoing the power rule. I could write u to the negative 1/2, go ahead and integrate that by adding 1 to my exponent and then dividing by that number as well. But key here, and the reason that I want to focus on this question, is that when we have actual limits of integration, when we do a u substitution, we need to change those limits of integration. These are x values. I cannot put the same values right here because I'm no longer integrating with respect to x. We have to change those values. So we have to look at our u substitution and say, let's get rid of some of this, that if x is 1/4, use this equation, figure out what u would be. If x is 1/2, use this equation, figure out what u would be, and those become your limits of integration. In this particular case, when x is 1/4, u is 3/4, and when x is, what was our top x? 1/2, u is 0. So we end up with this. Now, again, I'm not going to do just integration skills forever because you can do this in a calculator really nicely. But I do just want to show you one quick thing here, and then I'm going to show you what my calculator screen looks like. Remember the property that we talked about a couple of slides ago? If I flip the limits of integration and I negate my entire expression, I still have an equivalent statement. So notice that my limits of integration are going backwards. They're going right to left if you want to think about this on a graph. If I negate this entire thing, so if I take away this negative sign, this would be equal to 1/8 times the integral from 0 to 3/4 of 1 over the square root of u with respect to u. And for most parts, I'm going to assume you can throw these in a calculator and get an actual value if you need a value. So that looks like this. If you have not, and I know this is going to be some of you, if you have not actually used your calculator for integration all year, I am a high school math teacher. That would have been my class. We are very not calculator heavy people in my classroom. Not because my students like that, but because that is how I make it. If you have not touched your calculator to do integration really at all this year, play around with it a little bit to get more comfortable with it so that you can do quick integration and focus a lot more on the theory and interpreting the words of the free response questions and trying to figure out what in the world they're actually asking you and not getting bogged down with the algebra of finding the value of a definite integral. So if you have not ever touched that in your calculator, or if you just need a refresher, it's in the math screen. And then once you are in the math screen of your calculator, it's all the way down at number 9 on most calculators. It says FNINT, so function integration. And then that will allow you to put in an integral that looks like this. You will be able to physically type in the limits of integration and then the actual function that you are trying to integrate and the variable that you're integrating with respect to. It does not matter at all what that variable is as long as you have the same variable throughout your problem. Just to show you some things, I did this with an actual u and then made sure that I differentiated with respect to u. When you're typing into a calculator though, it can always be x. That's completely fine. The x button is easy, it's quick, all of that. If you want to be really, really fancy and type your fractions as fractions so that there is no room for error, you can do that as well. If you hit alpha, which on most of your calculators would be green, and then y equals, that will pull up a screen that has the first option as n over d, numerator over denominator, which lets you actually physically type a fraction like you can see here online. So just so you can see, these two integrals are exactly the same, 0.217. I also set my calculator as 3 decimal places because that's what an AP Calculus exam wants. Just makes it easier for me to remember and not mess up anything there either. You can, of course, do whatever you want with that. And then just to visually see here as well, when I flip my limits of integration, and then negate my expression, exact same values as well. All right, so here's our first free response question. And this is a question from the 2018 exam. So here, this question, we are looking at a particle. This is a physics kinematics question here. The particle moves along the x-axis with velocity function given by, or velocity given by the function above for time 0 to t to 3.5. So t between 0 and 3.5. Let's see if I can read math properly. The particle is at position -5 at time t equals 0. Find the acceleration of the particle at time t equals 3 and find the position of the particle at time t equals 3. Okay, the key to this question is not completing any skills. It's not asking, can you take a derivative? Can you find an integral? It's asking, essentially, if you know what it's asking. It's asking you to figure out the connection between this function and its integral and its derivative and all of these different pieces. This is not a skills question. It doesn't really care if you can type in a derivative into your calculator. It doesn't really want you to do that. It wants you to know the relationship. So if we start with a function chain here again, we can relate position, velocity, and acceleration, just like we related f and f prime and f double prime back in a couple slides before. Hopefully you remember the relationship between these three from your kinematics unit of calculus this year, or if you are in a calculus-based physics, this should be a common thing as well. So I'm going to go off to the side for this for a minute, and I'm going to draw red lines everywhere apparently. Okay, so we have a velocity function. We are given a velocity function, great. If I just start going through a velocity chain, so as I move down this chain of function by differentiation, I have a derivative of velocity and I have a second derivative of velocity, and I can keep going forever, but of course that's not super helpful to me. If I go up, I would have the integral of velocity with respect to t, and that's not great notation, but it's helpful enough for what we need to be doing. Now, think about what you know from physics, what you know from kinematics and calculus. We know that velocity is the derivative of position, and we know that acceleration is the derivative of velocity. So right now, I'm going to make an equality statement here and go over to another chain. I know that the derivative of velocity is acceleration. And now I can just start working through an acceleration chain. When I go down and differentiate, I end up with another equality statement. And when I go up and integrate, I'm going to end up with more equality statements. I'm not going to keep going up because we don't really have great easy notation for doing so, and we don't need it for this problem. Now, same thing with the relationship between velocity and position. Velocity is the derivative of position. I'm going to use s of t for position because that is just what I generally use in calculus. You can use other things if you're used to different letters from physics or from when you did kinematics in calculus. I know that position, when I differentiate it, gives me velocity. So velocity is equal to the derivative of position. And then I can make my position chain as well. If I'm going down from this function, I would be continuing to differentiate. I don't really need to keep going through this one, but we'll just go the whole way down to 3. And if I go up, I would be integrating. If I'm going up from just the first derivative, that would give me the position. And once you have something like that in front of you, once you have a function chain in front of you, whether we're dealing with kinematics, whether we're dealing with just F and G or whatever random letters we have, questions become really, really easy. We just have to figure out which piece we need and then do it. So here, I now want the acceleration, and all that I'm given is velocity. So I need to do everything in relation to velocity. So acceleration in relation to velocity is the derivative of velocity. which means that I need to take this velocity function and differentiate it. And if I want to evaluate that at time 3, I evaluate the derivative of velocity at time 3. Now, if you were doing this derivative by hand, this would be a quotient rule. There's no reason to do this by hand if this is on a calculator section of the old type of AP exam, which it was, or if you have a calculator in front of you for the new type of AP exam. You can do this, you can do differentiation in your calculator, just like I just showed you integration. It's the function right above integration in that math screen. And I will show you what that looks like in a minute. If we want position, we have to relate position to velocity. And I want position, which means I need to integrate velocity. This one becomes a little bit more to think about here, just a little bit more to think about, because we need to actually think about where we are starting. So in this particular case, S of t is equal to the integral of velocity of t with respect to t. That's going to give me a function. I want to get an actual number, an actual value, which means I need to make this a definite integral. And I want S of 3. So in order to do this, in order to kind of think through this, we need to think through the constant idea that is incorporated with this indefinite integral. And that constant is that original starting point, that initial condition. So we're starting somewhere, the position at time 0, and then we are going to go through the change of position, the integral of velocity from 0 to 3. Again, think about this like we talked about before. When I'm going from an indefinite integral into an actual antiderivative, I'm adding that plus c. I'm thinking through that extra constant piece. It's like working with an initial condition. And then once we do that, once we figure out what we're being asked to do, we just do it. We throw this in a calculator, get the numbers. Again, these questions require you to understand the connection between these functions and understand the ideas behind integration and differentiation and how they connect to each other. They're not concentrating heavily on, can you do these mechanics? Can you sit there and do a quotient rule for 15 minutes over and over and over? We can do all of that in a calculator. So if we do this, again, the derivative or the differentiation function, if you have not yet touched this in a calculator, is in the math screen. It's right above the integration function that we just looked at. And then we're truly just typing in that thing, that function we want to differentiate, and what value we are differentiating this at. We can only do differentiation in a calculator when we are given a specific value at which to evaluate that derivative. We can't get a function out of our calculator. When we do that, we get this nice negative 2.118. After I just told you I set my calculator in 3 decimal places, apparently I changed it. I still recommend that though. And then when we do this integration, this S of 3, so right here, this is the 0 to 3 V of t. That's going to give us this 3.2397-ish, this 3.24, and then we're adding that to S of 0. This is the change in position between time 0 and 3, but we still have to account for where we started, what that initial position was. We started at -5, and then we changed by this much, which brings us to this position. So there is our answer for acceleration and position. Again, calculator skills, good, we have to work on those, but figuring out what the question is asking you is that big priority. All right, one more piece here, which I think is going to answer a couple of the questions that I see in this question chat. If they don't, I will come back to those. So last part of this question, evaluate the integrals below and interpret the meaning of each integral in context of the problem. So evaluate the integrals, exactly what we just did. Great, here's your evaluation of the integrals. We can, let me take away everything that I've already scribbled here. We can go back, change our limit of integration to 3.5, and then we can also throw in an absolute value bar here. We can throw in absolute value bars and get both of these values fairly easily. The context, the interpretation and context is what I want to focus on. So remember from our chain of functions that the integral of velocity is position, and the conceptual idea of a definite integral is the net area under a curve from A to B. So net area, so the positives and negatives are canceling each other out. So this first integral here is actually just asking for the position or the antiderivative of V at 3.5 minus the position of at 0. If we actually wrote that out, it would look like this. I'm not going to use the notation of capital V because there's going to be very little difference between my lowercase v and a capital V. I'm just going to switch it right to S. We know that S is the antiderivative of V, just like capital F is the antiderivative of lowercase f. So really, we need to know the position at 3.5 and the position at 0 and subtract them. This is the displacement of the particle between time 0 and time 3.5. If you think about this geometrically using the velocity function, the positive areas under this curve are going to cancel out the negative areas. So we just have the net change in position. If we walked forward 5 miles and backwards 5 miles, they're going to cancel out to not changing. That's what we mean by net, the net change in position. So just the difference, the actual difference between the position at 3.5 and the position at 0, regardless of what happened between them. Displacement. In the physics world, this is displacement. When we change this to absolute value, that means that every one of those negative area sections, when we look at the graph of velocity, is going to turn into a positive area section. So there will be no cancellations between positives and negatives, or in terms of velocities, forwards and backwards. So in this case, we would be looking at the total change in position without forward and backward movements netting to 0. So that would give us the total distance traveled between time 0 and time 3.5. Even if some of those distances in terms of direction completely cancel each other out, that doesn't matter when we turn this to absolute value. If we want to think about that graphically, for those of you that are not giant fans of physics or just like to see things, if we look at this graphically, I'm going to completely take this into a different function right now. If we look at this, let's do a function like this. I'm going to try really hard to make these look similar. Okay, if we have, we're going to make this b and 0a. If I take the integral right now from a to b, this area and this area are going to cancel each other out. So really, my integral would just be this. If I take the absolute value of the area, or the absolute value, then this, let's just erase all the things. Stop. Okay, we're ignoring this now. We're going to change what I'm scribbling. This goes away. It moves to a positive. So in this case, oh my goodness. Oh my gosh, I'm just going to stop trying to write anything. In this case, I have a positive area, positive area, positive area. Every area counts as a positive value when we throw those absolute value bars on. Again, in terms of position, that means we're looking at total distance traveled, every single change in position. But if we don't have the absolute value bars, then that is allowing our positives and negatives to essentially cancel each other out. We're looking at that net distance traveled. That would just be displacement. All right, one more question. So question number 2, this is from a 2017 exam, and this one's going to incorporate some Riemann sums. So question number 2, a tank has a height of 10 feet. The area of the horizontal cross section of the tank at height h feet is given by the function a, where a of h is measured in square feet. The function a is continuous and decreases as h increases. Selected values are given in the table above. This problem is going to start with this first part here. I broke this one up into lots of different pages. This is going to start with this first part. Use a left Riemann sum with 3 subintervals indicated by the data in the table to approximate the volume of the tank. Indicate units of measurement. Okay, so we already have these rules for ourselves. It says use a left Riemann sum, use 3 subintervals. So we're gonna start with this. Okay, and really nicely, this is telling us what we're doing. This is telling us that when we integrate, essentially, this area function, a of h, we're going to end up with volume. So this is a fairly straightforward problem, but I want to call your attention to a little bit of notation here, so I'm going to go through this one. So volume of this tank, I'm going to call it v of h because we know that our variable is h. They are telling us that this Riemann sum is going to approximate the volume. So that tells us that volume is the integral from 0 to 10, tells us that 10 is the maximum in the question, of a of h. That is approximately going to be this Riemann sum estimation using left endpoints. Now, notice here, from this table, I have my first interval from 0 to 2, and I'm going to use the left function value as the height there. Then I'm going to go from 2 to 5 and use the left function value. Then I'm going to go from 5 to 10 and use the left function value as the height. These intervals are not equal. That's okay. This is what we're given. This is what we have to work with. So that gives us this approximation right here. We know that the width of my first interval will be 2 minus 0, and then I want a of 0. My second interval will have a width of 5 minus 2, and I want a of 2. And my third interval, will have a width of 5, and I want a of, which one do I want? 5. And again, that's because it says left in the question. Left is determining this part right here. If it said right, then I would use a of 2, a of 5, a of 10. But I don't want that. Now, here's the notational part. Pay attention to this part. When I start to sub in these numbers, this a of 0, a of 2, a of 5, that is a line that is directly equivalent to the line above it. So I want to flip back to using an equal sign. And if I just write these out here, so I'll have 2 times 50.3 plus 3 times, I know I took the table off your screen, I'm sorry, 3 times 14.4 plus 5 times 6.5. And then that is completely equivalent to, what does this one give us? 176.3. This is volume, so this is cubic feet. Again, notation, that may seem weird. I know a lot of students don't like flipping between these here. Once most students put an an approximation sign, they tend to just carry it through forever. But what's really happening is we are saying that this integral is approximately this. But this is exactly this. And this is exactly this. You're not restricted to using only approximations once you start. You always want to relate to the line above. If we read through this quickly, we're saying volume is equal to this, which is approximately this, but that's equal to the rest. Also, don't forget, this one was really super nice and reminded you, but don't forget units. Whenever you have units in a question, make sure that your units get into your answer. Okay, now, does the approximation in the part above what we just did overestimate or underestimate the volume in the tank? Now, because we had a function, a of h, that was decreasing, we used a left Riemann sum. That means that our approximation is going to be an overestimate. So this is an overestimate here, because a of h is decreasing. And that is a justification. We can add bounds if we want to. So between 0 and 10. That's an explanation. We don't need more than that. It doesn't need to be crazy. In any of these explanations, justify your reasoning, explain your reasoning, it doesn't need to be long. You can be as concise as possible as long as you are giving the actual correct answer. I know that sounds probably like a really silly statement, but don't think that you have to give 3 sentences or a paragraph or something that looks really complicated. You don't. Be as concise as possible. Give 2 words, give 1 equation. As long as it gives what you need, that's fine. If our function was increasing, a left-bounded estimate would be an underestimate. If our function is decreasing, like it is, and we used a right estimate, this would be an underestimate. Play around with just drawing rectangles all over functions and just kind of see if that makes sense to yourself. If a function is both increasing and decreasing, this is a lot harder to answer. All right, so let's keep on going. So here's the second part of the problem, or really third part if you want to think about this, the not Riemann sums part. Now they're going to make us connect the Riemann sums that we just did and actual integration. We just did an approximation for the volume of the tank. Now we're getting more information and we're being asked to refine our answer. So this question here, the area of the horizontal cross section at height h is given by the function above. This is a complete change to what we had in the beginning of the question. In the beginning, we had this area of the horizontal cross section is given to us by these values in a table. Now we're being told, actually, we know way more information. We have an exact function. So we already know that the volume is the integral of the area function between 0 and 10. We already know that. We already figured that out in the first part. So find the volume of the tank. Well, I already know the volume of the tank is the integral from 0 to 10, not t, sorry, I don't know why I wrote that, v of h, the integral of a of h dh. Again, we're being told that this area is now able to be represented by this function f of h. So instead of this, I'm going to write f of h because that is what the problem now says. And then I can say that this is the integral between 0 and 10 of 50.3 over e to the, what is it, 0.2h plus h. That is not, oh, sorry, and dh, don't forget that part. That is not something that's easy to integrate. Throw it in a calculator, get your number, and then we have it. Again, this is not a can you do this over and over and over type question. Most of the free response questions are not. They are, do you understand how to connect all of these pieces? And then can you just quickly do some math type questions. When you do this, just if you are super curious and want to know, this gives you 101.325 cubic feet. And now compare that to the estimation that we did and look at how different that is. All right, one more part. So part D of this same question, and then this is the end, I promise. So a seemingly unrelated question here. Water is pumped into the tank. When the height of the water is 5 feet, the height is increasing at a rate of 0.26 foot or feet per minute. Using the model from the part above, so that's still referencing this, find the rate at which the volume of water is changing with respect to time when the height of the water is 5 feet. This almost sounds like a related rates question. Seems very unrelated to what we just did, but it's actually really tying together a lot of what we talked about today. So let's write down what we know. We know that we're looking for a particular, or we're looking at a particular value of h, which is 5. I will try to keep this on the screen and still write out a legible way for you. We'll see what happens. Nope. Okay, so h equals 5. We know that h equals 5. We also know the rate of change of h with respect to time. I know that dh over dt equals 0.26 feet per minute. We know that area as a function of height can be written using the function model at the very top. So I'm just going to copy that down to the bottom. So I know that area, A of h, is my f of h. That is 50.3 over e to the 0.2h plus h. And then let's see what else we know. And we want to find the rate of change of volume with respect to time. So we want the rate of change of volume with respect to time. That's what we want. All right, so here's the connection piece. We have all of this information. How in the world do we relate to that? How do we get from this known information about height to using area to find a rate of change of volume? And this comes from the information that we had in the question part above. We know that volume is the antiderivative of area. So when we integrated area in part C above and part A, we got volume. Volume is the antiderivative of area. So we therefore then know that area is the derivative of volume. Area is the derivative of volume. So area is the derivative of volume with respect to the variable in question, which in this particular case is h. Area is the derivative of volume. Here's the connecting piece. Here's the part we need to finish anything in this question. Now, let me just pause and say, this is not a blanket statement. This is in the context of this question. Volume and area don't have this relationship all the time, like position, velocity, acceleration. That's in this question because we were told volume was the derivative of the area in this question. That is not just a 100% all the time thing. Anyway, we know that area is the derivative of the volume. So I'm going to take out this middleman here. We don't even care about that. And say, great, now I know that my derivative of volume with respect to height is equal to this function. That's almost what I want, almost. I just want one little tiny manipulation, and I want the rate of change of volume with respect to time. So if I take what I know and I differentiate it, so now I need to differentiate height with respect to time, and I do that on both sides of my equation, I will get what I want. So think about this two different ways. You can think about this purely mathematically. If I do the exact same thing on both sides of an equation, my equation still holds. Pretend you're multiplying both sides by 3. Your equation still holds. What's actually happening here on this left side is that we're kind of working through a chain rule. I differentiated volume with respect to height, but now I need to differentiate height with respect to time in order to actually get the derivative of volume with respect to time. And then that would equal all of this times, we know this number, 0.26. And we want to evaluate this at a specific point. I want h to be 5. Throw in a 5 right there. We're going to get a number. And when you do that calculation, we get 1.694 cubic feet per minute. So again, all of these questions, or hopefully you can see that most of these questions, become really calculation-wise simple once you know what you're being asked to do. The connection between area, in this particular case, area and volume, in the question before, velocity, position, acceleration, the connection between a function and its antiderivative and a function and its derivative is what's really important here. So that's the last question for today. Oh, sorry. This is what we just talked about. I'm going to come back on and there's one more outstanding question that I want to try to answer quickly, if I can. If you do not have any more questions, or your questions were all answered, you are welcome to log off now until next week. I loved doing calculus with you again, and I hopefully will see you again next week. Oh, quick thing before that. I am going to do a BC section that has just information that's on the BC exam that's not on the AP exam on Friday. So you can get information about that on the Prep Matters website as well. Again, if you don't have any more questions, feel free to log off. I will see you again later. There is one quick question here about S of 3.5 and S of 0. That represents the actual, so S was my position. That represents the actual position at time 3.5 and position at time 0 of the particle. So where it actually was on the number line. And then, is there a more broad step-by-step process that can be taken for the last problem? Kind of, yes. I will rope that into the next session for you. I will start with that and do a longer review of that type of question with a more step-by-step process. If you want more detailed information beforehand, just send an email to the classes@prepmatters.com and I will get that right back to you. So have a great week, everybody, and I will see you again next week.